Hi class, in this video here, I'm going to do a very quick introduction to section 4.3. And the title of this section is The Sexiest Rectangle. And it's about finding aesthetics in life, art, and math through the golden rectangle. And we've talked about the golden ratio before in a previous chapter. And now we're going to talk about how it relates to geometry here. All right, so what's going on in this section? It's about rectangular appeal. And so what are the dimensions of the most attractive rectangle? All right, so the rectangle we might imagine when we close our eyes on a dark, starry night and dream of an ideal rectangle. All right, when someone says rectangle, we think of a shape. What shape is it? All right, so kind of like from the rectangles given here. So imagine you see these four right here. Okay, choose one that's most appealing to you. So they're all rectangles, right? And it's a very subjective thing, and not everyone's going to say this answer. But given these choices, a high percentage of people, all right, surveys have been done about this, think this second rectangle here from the left is the most aesthetically pleasing. Okay, and this is the one that captures the true spirit of rectangleness. Okay, this rectangle here is referred to as the golden rectangle. It is the length of the base relative to the length of the height that makes it the golden rectangle. So there's something about like the ratio of the base to height here that make it so appealing of some type. All right, so what precisely is the ratio of the base to height that produces the golden rectangle? All right, well, recall that in our conversations about numbers, we found a ratio that was an especially attractive number. Okay, that ratio rose in our discussion from in the again previous sections of this Fibonacci numbers. And we denoted it by this Greek letter phi. All right. And it was called the golden ratio because it satisfied the symmetric equation of ratios. All right. And so the golden ratio gives us this satisfying relationship of height to width for those rectangles that many deem extremely pleasing to the eye. And so the precise mathematical definition of the golden rectangle is any rectangle having base B and height H such that when you take the ratio, okay, of the base to height, and now the base and height can flip. So basically, you're going to see when we do some examples of this golden ratio that the higher number is always going to go in the numerator, okay? And this golden ratio is roughly one, or it's 1 plus the square root of 5 over 2. And if you plug this into your calculator, this number is 1.618, repeating. And for whatever reason, this ratio, okay, is just for most people the most aesthetically pleasing ratio of a rectangle of its base to its height. All right, so where do we see these things in the natural world? So if you think about the Pantheon in Greece, all right, and you were to look at constructing a rectangle around it, this Pantheon, right, beautiful structure here, okay? Turns out if you have this be the base and this be the height, so kind of think of it as a rectangle on its side here, all right, the ratio there produces a golden rectangle. If you think about Leonardo da Vinci's sketch here, right, with embedded in this right here is the golden rectangle. This right here, you might not recognize this building, but this is the United Nations building in New York City. This right here, this shape here, that when they designed it, the proportions were that of a golden rectangle. Okay, so and it's in a very aesthetically pleasing rectangular shaped building here. And so where else do we see this? Okay, we see this also in these things called golden spirals. And we close with one last aesthetically pleasing construction. So let's take a golden rectangle. All right, so I know it seems weird to see it, but like let's start way in here, golden rectangle, right in the beginning, okay? And start drawing successive squares. So what I see is along the side, I add a square to it, okay? And that square has the length and width of this side of the golden rectangle. And then I do it again. Well, this right here, when I add a square to it, it produces another golden rectangle, believe it or not. And then we do it again, add another square. Got another golden rectangle. Do it again, another golden rectangle. Add another square up here, another golden rectangle. And I'm going to keep doing it, all right? So within each square, we will draw a quarter of a circle having radius equal to the side of the square. And if we keep doing this, we'll get this beautiful golden spiral. And this is also something, you can see the spiral shape here, that is naturally occurring in the real world. So this shape, this idea of the golden ratio, all right, not only comes up in rectangles, but you can see it here in this a seashell. All right, let's end this just by talking with one Mindscape problem. And so it asks this: which of the following objects most closely resembles a golden rectangle? So if you think about index cards, you have a 3x5 index card, 4x6, and a 5x8 index card. Okay. If you wanted to see which one most closely resembles the golden rectangle, you'd look for that ratio, okay, of the base to the height. Okay. In which case you'll always put the higher number in the numerator. So if you look at 3x5, the ratio here is 1.667. That's just like going back. This is the golden ratio. It's like roughly 1.62. If you look at the 4x6, its ratio is 1.5. And if you look at that index card, that 8x5, its ratio is 8 to 5, which is 1.6. This is the one closest to the golden ratio. So this one here would be the closest. The biggest actually index card here would be closest to the golden rectangle. And now this was just a super quick introduction to this concept. And in your readings of the chapter here, it'll dive a lot more deeper into this, talk about proofs of specifically this spiral. But as always, I'm here if you have any questions or concerns.